Swayam Prabha. Digital India. Educated India.
Welcome to the organ printing course. So in the last 2 weeks, we have discussed different bioprinting techniques, the characteristics, process parameters, advantages, disadvantages. Also, we have done comparative analysis of different bioprinting techniques. In today's lecture, basically, we'll discuss Bioinks and their role in bioprinting. So we'll start with Bioink. What is Bioink? What are the different types of Bioinks possible? And what are the important characteristics of Bioinks for 3D bioprinting or for organ printing? So let's start with Bioink. And as I have also earlier mentioned that Bioink is the most vital ingredient of bioprinting because this is the bioprintable formulation. So when we make a polymer or polymer solution or hydrogel, we also incorporate cells or other things in that, and then if we use that for bioprinting, then we can call them bioink. So bioink is nothing but a bioprintable formulation. So it can be cell laden hydrogel. So hydrogel is when the cells are embedded or encapsulated in a hydrogel, and then it is that mixture is used for bioprinting. Then we call them bioink. So here sometimes some bioactive factors or bioactive molecules are incorporated, or they may not be incorporated or encapsulated within the bioink. So this is the most vital ingredient, as you must have understood that for bioprinting we need bioinks, and these bioinks, and most of the time these bioinks are very specific for a particular applications, like for particular target tissue we use that tissue specific bioink. So where the specific bioink that supports the growth or function of that particular cell types or cell or the different types of cells to develop a certain tissue structure, right? So what it does, so because if you see the bioprinting, when we use this bioprintable formulation or this hydrogel, cell laden hydrogel, that mixture has to be loaded inside the, either in case of inkjet or extrusion based bioprinting, that cell laden hydrogel, that mixture has to be loaded inside the syringe or not cartridge or nozzle, right? So in case of uh, laser assisted bioprinted, again it is coated in the form of ribbon, right? In both these cases or in all these cases, the condition is unnatural. That means the cells are not used to this kind of environment. We are putting them in this environment. So that's why the cells, when we generate bioink, we try to provide all the necessary conditions or is kind of a microenvironment to the cells, so that it is a suitable ambience is provided to the encapsulated cells, so that the cells can survive, they can function, or they can do their job, like they can grow in number, they can differentiate, they can migrate. So all these things made possible by using certain bioinks that supports all these functions. So bioink is a, as I said, so bioink is a bioprintable formulation or it's a cell laden hydrogel. It may or may not contain bioactive molecules or bioactive factors, and it provides a suitable ambience to the encapsulated cells, and also it supports the cell viability and cell functionality. So that's why bioink is very important. And when we use some bioink or when we develop bioink, we take utmost care to prepare the bioink in a certain way, so that the bioprinting process is effective, so that the cells survive this bioprinting process, and then it can be used for other things. So we'll see what are the different properties of bio Biowink that is important for biofabrication. And in this slide I have taken this example of because mostly for bioprinting or bioink development we use some hydrogels, because hydrogels are a type of materials where they possess or they contain lot of water, right? So it's a water rich environment. So in that actually the cells can easily survive and they can function. So that's why mostly we use hydrogels for making different bioinks. So in this thing here we'll discuss what are the key hydrogel properties that is required for biofabrication, right? So any bioprinting process or biofabrication process where suitability of a particular hydrogel typically depends on that particular application or biofabrication, and for that particular application, what kind of physiochemical properties is required. So, and then we match those physicochemical properties with some different biohydrogels, and then we select a particular hydrogel for a biofabrication process. So suitability of hydrogel for a specific biofabrication process mainly depends on the physical chemical properties of that particular tissue, right? So when we select a tissue, we try to see the physical properties of the tissue, like the tissue, whether the tissue is what is the softness or hardness level of the tissue, what are the different composition of the tissue. So the physicochemical properties of the tissue is very important to understand while selecting for a particular bioink or a particular hydrogel. But one challenge of bioink development for certain biofabrication for specific biofabrication approaches, because here we have to satisfy both the requirements in terms of fabrication requirements and also in terms of cellular requirements. That means for fabrication we need certain type of or certain physicochemical properties of the bioink, but for cell culture the requirement is very different. So that's why it's a challenge to suit or to match both these things during bioprinting, right? And the hydrogel printability of the hydrogel, that mostly depend on the physiochemical properties. The major physical properties that determine the hydrogel properties are rheological properties and cross-linking mechanism, because now we must have understood that, or in the last few lectures also I have stressed on this, that the bioink, the most important property bioink is when they are inside the syringe or inside the before extrusion, they should have this flowability, so that they should flow through the nozzle and they should come out upon application of pressure. But as soon as they come out of the nozzle, then they should start solidifying, or so that the shape can be retained, the structural resolution can be maintained, or the printing fidelity can be improved, right? So that's why cross-linking is another important part of this different biofabrication approach, because rheological properties will decide how the material comes out of the nozzle, like what is the flow, how the material flows through the nozzle, through the syringe, through the nozzle. But cross-linking will help to solidify the material upon deposition or upon extrusion. So that's why these two are very important physical properties that determine the printability of the hydrogel, or bioprinting capability will very much depends on these two properties. And if you see in inkjet printing, mostly you work with low viscous material, right? So the inkjet printing there, the low viscous materials is the major thing. So there, that's why there, as soon as the drop, suppose you are interested to bioprint certain structures with inkjet printer, then as soon as the material comes out of the nozzle, when it deposits, it too should solidify very fast. So that's the requirement for inkjet printing. Inkjet printing limited to low viscosity, so we use low viscous materials for. But in extrusion based bioprinting, may use higher viscous materials. That has some advantages. We'll see what are the advantages when you use high viscous, when you use low viscous, what are the disadvantages of this in case of bioprinting. So inkjet printing requires rapid gelation to allow fabrication of an intricate 3D structures, because in this case the viscosity is very less. And bioprinting with high viscous liquid materials. Yeah. So bioprinting with, when we use high viscous liquid materials for bioprinting, that what it does, it helps to retain the shape after deposition, right? So that's the advantage in case of extrusion bioprinting, because in case of extrusion bioprinting we use high viscous material. So when high viscous material comes out of the nozzle, and as soon as it comes out, and that time, because of this high viscosity, it initially it maintains the shape after deposition, and it allows you to do the gelation or cross linking after fabrication. So post fabrication cross linking is possible in case of extrusion by printing, because of this, because we can use high viscous material. But if the material viscosity is low, then as soon as it's come out, and when you deposit that, it started spreading. It starts spreading, so that the shape cannot be retained. Basically, we get a deformed structure. We can get, if in case of, that's why in case of low viscous material, high gelation or rapid gelation is very important. But for high viscous material, slow gelation can be used, can be utilized or employed, because the, the high viscosity that retards the shape deformation, right? Other thing is, in case of the hydrogen, when you are using hydrogel for bioink development, for biofabrication, that time also we need to understand the swelling behavior or deswelling behavior of these hydrogels, because this hydrogel, all the hydrogel material, they either they swell if we put them in, if they put them in buffer or media, or they may deswell. Right? So we need to understand, we need to study these two properties and advance to know that what is the swelling behavior or deswelling behavior of this hydrogel before bioprinting. The other thing is also we need to take care. Suppose in certain bioprinting applications, there, suppose we may need to use two different types of hydrogels, or more than two different hydrogels. So that time we need to understand the dissimilar swelling behavior, because each of these hydrogels, they have the specific swelling behavior or deswelling behavior. So that's why this swelling or deswelling behavior may mismatch. So that's why we need to take care of this thing when using different bioinks with different swelling behavior. So these are the key hydrogel properties that we need to understand for while developing bioink for biofabrication. So we'll discuss some of these properties in details. Like, these are the key hydrogel properties that in the earlier slide also we have discussed. So here again I have listed those properties, like the rheology, viscosity, shear thinning property, yield stress. These are very important for hydrogel material, because all these have very high influence on the printing capability, or even on the cellular cell viability, cell functionality. All these things, these hydrogel property, they influence a lot. Other this thing again, as we mentioned, cross-linking mechanism for hydrogels, that is very important. And in the later slides, we'll discuss each of these things. We'll discuss in great detail. So in cross-linking mechanism, where actually we can cross-link the structure either by physical means, like either by, suppose, ionic cross-linking, thermal cross-linking, or stereo complex cross-linking. All these things are very important for when we actually use this physical cross-linking for hydrogels, because each of them have their own advantage and disadvantages. Chemical, in case of chemical cross-linking, also chemical cross-linking is, this process can be little slow, but chemical cross-linking actually help helps in further stabilization of the structure, so that the structure deformation and structure stability can be improved further. Similarly, photo cross-linking is another important area where it is used for different bioprinting applications, like to stabilize the structure, to retain the for shape retention, for structural fidelity, for structural resilience, for structural stability. All these things, different cross-linking mechanisms are used. We'll discuss this in the later slides. So let us first, before even actually discussing what are the different hydrogel properties in great detail, let us understand what are the ideal material properties that is required for bioprinting. Right? What are the different, and this, as I earlier mentioned, the selection of appropriate materials for use in bioprinting and their performance in a particular application depends on several features. Depends on several features like how you select a material for bioprinting and their performance of that material for particular application. That can be that can have several factors depending upon the type of material you select, right? Because now printability is the major factor for bioprinting. Right? The material should be printable, otherwise we cannot use them for bioprinting. Right? So whatever the material we use for bioprinting, biofabrication, the material should have printability, sufficient suitable printability, so that the material should come out through the nozzle in an uniform manner, and then it should, when we deposit that, the deposition process should be uniform, so that we get the required resolution, the exact geometry that we suppose that the design has been made. So as per the design, we can get the exact time. So printability is a major factor for bioprinting, and so the printability of hydrogel is a major is a, the property. So the material should have ideal printability. So and for a material to have printability, all these are again important factors that contributes to the printability of a material. Like viscosity, it plays a major role for to decide the printability of a material. So based on the viscosity, either the material is printable or not, that depends on the viscosity. Like if you use very low viscous material, the material can come out of the nozzle very fine. But then the material will start deforming and will not be able to make a very good structure. So printability would be compromised when you use. Similarly, if you use very high viscous material, there also we need to exert a lot of pressure to to print the material, to extrude the material on the print bed. So that is another important. So that is another important concern. So viscosity. So viscosity, we need to choose a viscosity that is depending on a particular type of material. The viscosity can differ. There can be different viscosity have different level of or different level of viscosity can be used. So viscosity is better. Then gelatin method, as I already as the earlier slide we have mentioned, that the after extrusion the material has to be solidified. So the gelatin method is very important. So the gelatin method can actually gelatin process can start before deposition, but the material should not be fully cross-linked before extrusion, because otherwise it will prevent the extrusion of the material. So that's why gelatin method is another. On what type of gelatin method, how fast or the rate of gelatin is also important, right? And then the rheological properties we have discussed some of the things. Again, we'll discuss more about the rheological properties. Those are very important for bioprinting, right? Then the biocompatibility of the Biowink. This is another important material properties. Like the way that the material, whatever the material we choose to develop the Biowink, those materials should be biocompatible in nature. And what is biocompatibility? Biocompatibility means these materials should not exert any undesirable, or should not possess any undesirable local or systemic responses. That means they should not they should have desirable local or systemic response. They should not be toxic to the body. So non-cytotoxic is very important. They should not be toxic to the body. If they degrade, their degradation product further should not be toxic to the body, and they should allow cell attachment or cell proliferation, cell migration. All these things, those are very also important. So basically, they should support new tissue formation. That means in case of tissue regeneration, how the new tissue forms, that is the cell, the material should support new tissue formation. It should not obstruct, or it should not hamper the new tissue formation. It should support the new tissue formation. That then only we can able to use them for bioprinting, because in bioprinting also our ultimate aim is to develop artificial tissue and organ, right? So if the tissue, if the cell is the tissue is not growing, if the new tissue is not forming, then that kind of bioink is now not useful. There are more properties in this thing, like the degradation kinetics and byproducts. So the material, when you use certain material, the degradation rate of that material should match with the ECM production by the cells of that particular tissue structure. Like that should, so that means when we use them, that thing for tissue engineering, because in tissue engineering what will happen, the whatever the provisional extracellular matrix that we use in terms of biomaterials, that would degrade, and then after some time, and simultaneously the cells, they will produce their own extracellular matrix. So these two rates should match, the degradation rate of the biomaterials and the ECM production by the cells. That means the degradation rate and the tissue building, both these things should go at the same rate. Otherwise, there will be a mismatch, and then that can be a challenging thing. Other than this, the degradation products of this biomaterials, they should not be toxic to the cells. So all these different degradation byproducts, they should not be toxic to the cells. Any, because these biomaterials, when they degrade, they can produce certain byproducts. The most important thing is the biomaterial as such and the degradation product, both should not be toxic. And then the other thing is, all these biomaterials, they should have a suitable swelling or contractile characteristics. That means these bioink or these biomaterials, they can swell or diswell. So that properties should match with the tissues like thing. So because the swelling behavior is also very important, we need to study them that in details. Then there are certain structure and mechanical properties of the biomaterial, that is also important, right? Like when we choose some biomaterials for some particular tissue engineering applications or particular bioprinting, then always we match, or we try to understand the physical chemical properties or the mechanical properties of that particular tissue. Accordingly, we choose a material, or we choose the concentration or of the material accordingly, so that the mechanical properties of the construct should be matched. So materials should be chosen based on the required mechanical properties of the construct. That is very important. Other than this, in terms of chemical, the material biomimicry, like the material should be able to chemically match the chemical properties or the composition of the tissue. That means material wise, chemistry wise also, the material should be matching to the tissue ECM or extracellular matrix, because the materials are mostly, they will be used as a provisional extracellular matrix. So the materials should mimic the chemical nature of that matrix, so that the cells, when you put the cells on the bioink or the material, then the cells can withstand, or cells can experience similar chemical milieu or or similar microenvironment, so that they can grow, they can function. Right? The other thing is structure and functional and dynamic material properties. Like the structure of the material is also important, because, and the mechanical properties of the material, that is another. Those are important to understand, because they can have they can influence the tissue building process or the bioprinting process also. So that materials, we have to understand the materials. And then other thing is the tissue specific material composition. Because each tissue has their own composition, right? So we need to understand what is the composition of the particular tissue. Accordingly, for bioink development, accordingly we need to employ certain materials, so that they can match that particular tissue compositions. Right? So these are the ideal material properties of bioprinting that we need to consider before actually even going for this typical similar particular type of bioprinting. We need to understand all these properties. So thank you all of you. In the next lecture, we'll discuss each of these characteristics in great detail. Thank you very much. So after going through this ideal material properties of for developing biowings for biofabrication, let us understand so the important requirements for selecting a biowings for 3D printing. The biometry in terms of the biomaterials. Like the very first thing that we have discussed for developing any biowing for 3D bioprinting is the printability of the bioink, right? The printability of the bioink, as we have already discussed, the material should be able to use for bioprinting. Like the printability of the material should flow during the printing process, and after going through then after going through the printed after extrusion or after upon deposition, the material should be start able to gelatin. The printability of the material is the base first thing. Then the biocompatibility of the material. So the material should be biocompatible so that we can be able to use that. The next thing we have also discussed the biodegradation of the material. That means the material should be degradable at in physiological condition. That means when we use that material for certain applications, the material should degrade and the degradation products should not be toxic to the cells. So the non-cytotoxicity of the material and the degradation product both should not be cytotoxic. Then the other thing is, as the material comes out of the nozzle, this should be the gelatin should start, or the solidification of the material, solidifying of the material is very important. So that is another criteria, important requirement. So the material should be able to get gel by any of these such means, either it can be physical, chemical, or photo. So the material should be able to form gel. So gelatin is another important criteria. Then we have discussed, because all our tissue, if you see most of the all our soft tissues or even some hard tissues are they are viscoelastic in nature, right? So they have both viscous and elastic properties. So that's why they so accordingly whatever the materials we use for bioprinting, like the most all the materials, they should have this viscoelasticity. Okay, so they should have both the viscous and elastic behavior. Both these things biomaterials should possess both this behavior, and then they should be able to be used for bioprinting of certain tissue structures. The other thing is this, for survival, all this survival, the cells need oxygen, nutrients, all these things. So the whatever the biomaterials we are selecting for bio development, that biomaterials should support oxygen, oxygen diffusion, nutrient permeability, so all these things. So oxygen and nutrients should be able to diffuse through the biowing, so that the cells, when they are embedded or encapsulated within the structures, so then they should be able to get fused. They should be able to get the oxygen and nutrient so that they can survive. The cells can survive. The other thing is the shear thinning behavior of the biomaterials, as we have discussed earlier, that for extrusion based bioprinting, typically the material should have shear thinning properties. Shear thinning means with increasing in shear rate, the viscosity of the material comes down. That means it's a non-Newtonian behavior of the material where the viscosity decreases with increases shear rate, right? And it is helpful for extrusion based bioprinting, because in extrusion based bioprinting, when we extrude the material, we apply force on the material. So when we apply force, that shear rate increases. So due to that, the viscosity decreases, and the material can easily come out of the extrusion nozzle. So shear thinning behavior is another important requirement. Then the material should support tissue regeneration, because when you use some biowing and we incorporate cells or encapsulate cells within this biowing, then this biowing provides the necessary microenvironment or support structure to the cells to function, like grow, mature, migrate, regenerate. So the tissue regeneration process can happen if the cells are healthy, they are doing their function that is required. That's why the bioink, whatever the bioink we material we select to develop bioink, that should support tissue regeneration, because that is the ultimate goal of our all bioprinting process, to develop a tissue, artificial tissue or organ. Then also the remodeling, as we have discussed earlier, that the biomaterial should be degradable. So that means the biodegradable, when after bioprinting the structure, the biomaterial degrades, and it keeps space for the cells to produce extracellular matrix or to deposit extracellular matrix, right? So that degradation of the material and production of ECM by the cells, both these things, both the rate should match. That is, so that the tissue, we are the material allowing the cells to remodel the structure or to remodel the tissue. That means a new tissue is growing and the printed structure is getting degraded, or printed structure, that means the printed biomaterial structure, that is getting degraded, but a new tissue is growing in that space. So that is remodeling, and that is very important for new tissue building. So biomaterials should be able to provide all these things. So these are the important requirements that we discussed, like the printability, biocompatibility, biodegradation, gelation, viscoelasticity, oxygen nutrient permeability, shear thinning behavior of the material, in tissue regeneration and remodeling. So all these are very important requirements for any bioinks to be used for bioprinting. Thank you very much for attending this lecture. We'll see the rest of the thing, like the other bioink properties in great detail, each of these bioink properties in great detail in the later classes. Thank you very much.